Hello, hi. Welcome to Tech Talk by Kevin Kelly. This talk is going to be available on Google Video, and so we ask that you hold questions that are proprietary at all to Google until the end of the talk. So, Kevin Kelly is well known around the world as the editor-in-chief of the Whole Earth Review and is the author of the book Out of Control: The New Biology of Machines, Social Systems, and the Economic World. Today, Mr. Kelly shares his ideas on the future of science and the scientific method. He's come to the right place because Google has an important role to play in the future of science. Join me with a warm welcome for Mr. Kevin Kelly.
Thank you. It's a real pleasure being here. In addition to being editor and publisher of an obscure magazine called the Whole Earth Review, I was also one of the co-founders of Wired magazine. And for the 5 or 10 years that Wired was the center of the universe, it really felt great. And being here at Google feels like that again. It feels like I'm at the center of the universe again. And I use that in a kind of metaphorical way, but also in a very real sense. I define the center of the universe as that place where there's the least resistance to new ideas. And I feel that in some ways this is the center of the universe. And it's a real privilege to be talking at a place where there's probably the least resistance to new great ideas. And what I want to spend a few minutes this afternoon talking about is something that I think is very important but gets very little attention. And that is the nature of the scientific method. And I'll start there, and I'll kind of end up at some cosmic level. And I hope you kind of go along for the journey. I think that it may have some bearing to what you're doing in the long term. So in addition to also running the co-founding Wired magazine and being editor for many years, I also am in one of the small group of people who have been pioneering long-term thinking. We have a foundation called the Long Now Foundation. Among other things, we're trying to build a clock that ticks for 10,000 years. And the idea of that clock is to serve as an icon and an encouragement to think long-term. So what I'm trying to do a little bit in this talk is also take a very long-term view of things. Rather than just thinking of the last 5 years and the next 5 years, I'm trying to stretch our perspective and go back 1,000 years and maybe look forward to 50 years. It's kind of asymmetrical, but that's the best I can do in terms of the future. So what's interesting about science is that science is the only thing that generates news. Science is really the only news. If you pick up a paper, most of the stuff that's happening is not really news. It's just kind of a repetition, a little bit of a recycling. But science is the thing that generates real news. What's interesting about the news that it generates is that it's often novel. And when we tend to think of the long-term history of, say, the scientific method or science, we tend to think of the inventions that science generates. And as an exercise, we sent a questionnaire around to a bunch of scientists around the world and said, what's the most important scientific inventions in the last 1,000 years or the last 2,000 years? And you come up with a list, and you can make your own list, but some of the nominations for the most important scientific inventions or the most important inventions over the last couple thousand years was, let's see, how does this work here? It was hay. That hay was actually the most important. This was actually Freeman Dyson's idea, that actually encouraged cultivation of domesticated animals, which led to protein, which led to a longer lifespan, etc., civilization. So that's one. Another one is antibiotics. That was a really interesting and great and important invention in the history of the world. Paper. Who could argue against paper? And of course, this ancillary technology of printing. That was obviously a very important thing. The rudder allowed navigation of the world and a sense of the whole world and encouraged trade. So that was also very important. And electricity. Obviously another very interesting thing. Once we harnessed the electrons, all kinds of other great and wonderful things happened. Now, what's important about that is that you can make your own list, and that these are different inventions. But I'm actually not really concerned about that, because science makes news, but we very rarely look at science itself, the method by which these things come about. And that's what I'm really trying to do. And so if you actually suggest to someone that the method that we know of as science today is still changing, and that in fact the scientific method may in fact be very different 50 years from now than it is today, this is the kind of reaction you normally get. Because when we talk about the long-term trend of the scientific method, I find that people are very puzzled. I mean, this is sort of like science changing. Science will be different in 50 years, the scientific method, and I think it will. And so what I want to do is kind of take a quick tour through the evolution of the scientific method in the past. And interesting, when I went to look at this, I found that basically there is no literature on this. There is no book about the history of the scientific method, and for something so fundamental, you would expect that, but there isn't. So I sort of cobbled these together, and I'm going to go through very quickly, just to give you a sense of sort of some of the things that I think are important. And one of the patterns that you'll see, I hope, is that this is a lot about information. We have the idea of indexing and cataloging. Books have been around for a long time, and then you have this idea of indexing or cataloging the information. So, or you have a book that is the index to the other books. And so actually some of the great inventions in the history of the scientific method was the idea of an alphabetical index, was the idea of having an index in a book, was the idea of having a catalog to all the books in your library. Then there was the collaborative encyclopedia, where you had more than one author, more than one expert coming together, sharing information, and in such a way that it was all cataloged and indexed. There was, later on, several hundred years later, there was the first laboratories where they began to do experiments, actually trying to observe and measure and record those observations. We had the invention of observational tools like the telescope and the microscope, which greatly enlarged the scientific method, because I, along with some other people, believe that the tools of science actually move science more than any other discoveries of science. That in fact, the way in which you have progress is by the creation and progressive improvement of tools. Then we had, I'll take it out of order, we had the controlled experiment, which was Francis Bacon's idea that one needed to have controls. To do an experiment, you have controls. There was a society of experts that began to share the information and the observations they were making, so they began to actually have kind of a peerage. And then there was, oops, they got cut off. I had a problem here, but this is Bolton's idea of that in order to do, that real science required that you be able to repeat an experiment, that someone else should also be able to do it at the same time that you are. Peer review, where they began to actually send out their observations and have them peered, reviewed by people who knew about it and could either give them credibility or verification. And then this is Newton's hypothesis prediction, which actually he was making a prediction, making a hypothesis about something and making a prediction that you should find data at some point. Falsifiable testibility, Popper's idea that what really counts in terms of a prediction is whether it can be falsified, that's the sort of criteria by which you judge a hypothesis. Then Fisher, in the randomized design, he was involved with statistical analysis, bringing statistics into the design of an experiment. The placebo, somebody actually had to invent that. That was not an obvious idea. It took many years. It was actually fairly late in coming, 1937, before the first placebo experiment was done. And computer simulations, I'll talk a little bit more about that, began very early. Almost as soon as computers were invented, they began to do simulations. And then the double-blind refinement where you actually have both the observer and the patient not know about the experiment. And finally, I think a very landmark moment was where science began to study itself, where the scientific method became a subject worthy of the scientific approach. So one of the things that's interesting about this is I began to think about, what about China? Now the thing about China is that it did not discover science, but if you take a list of all the technological inventions that China made, it's phenomenal and actually very unknown in this culture. Most of the technologies that China discovered, they discovered not just a few years before the West, but often on average, maybe 500 years to 1,000 years before the West discovered it. So it was very independent, and yet they did not originate science. And what was missing? Well, first, here are some examples of the things that actually were discovered in China. Paper, printing, gunpowder, compass, the rudder, the stirrup, row crops, iron plow, wheelbarrow, cast iron, vaccinations, the chain drive, suspension bridge. They were using petroleum and natural gas as fuel. Again, thousands, at least hundreds of years before the West came to this. And actually going back to Francis Bacon, when he began the scientific method, believed that 4 inventions had more impact on science at his time, this is around the 1600s, than anything else. He said these 4 inventions, which were paper, printing, gunpowder, and the compass, he said, transformed our world far more than any religious belief, far more than any political or warring, conquering nation, that those 4 inventions, which he said, whose origins are unknown, were the transforming powers in his world. And he died before he discovered that all 4 of those inventions came from China. Now, so why didn't the Chinese invent science? And there is actually no easy answer to this. A man named Joseph Needham devoted his entire life to trying to answer this question, and it's now called the Needham question, which is, how could science and technology, which was so far advanced in China for so long, how come China did not actually continue going that way and actually come up with a scientific method? And the answers, as I said, are very complicated. There's numbers of strands to it. Part of it had to do with an inability to separate the political and the inquiry, the religious and the inquiry, and a sense of maybe valuing other things besides a quest for truth as a proper form of investigation. All those kinds of wrapped together to lead to what happened was that there was one discovery that China didn't make, and that discovery was the scientific method of discovery. So it was just, you can go a long way with creating novelties, actually having progress by developing new ideas without the scientific method, but the scientific method is the best way to do discovery. And once you make that discovery, you're off on a different course. So I tend to think of science as a structure of information that allows discovery, as a structure of discovery. And this is just a kind of a mapping of the citation indexing. This is a mapping of what they used to call in library science citation indexing, which we would now think of as almost as a type of page ranking of scientific discovery. So they would look at the whole of all the citations that were referenced in the footnotes of a paper, and if you extract out a map of those backward links, you would get something like a clustering of those journals or those individuals who were cited the most, basically that were linked to the most. And this work was done by Eugene Garfield in the 50s in Philadelphia, and it was somewhat the inspiration that Larry and Sergey looked at for their page rank. And if you take this structure of scientific discovery, just as an example, and think about it as a way of structuring knowledge and information, as a way of knowing. That's the view that I want to bring into what science is. It's a way of knowing. More importantly, it's actually a way that we change how we know. And I think, I hope to end up with, return to that idea that in fact it's not just the process of discovery, it's the process of how we change how we discover, because there is a second order. There's a second order delta in science. It's not just studying things, learning new things, it's changing how we learn new things. It's learning how we learn new. It has that recursive sense in it. And I think that's really crucial, because it's that recursiveness that actually gives us generative power. Almost all the things that we find interesting in the world have a sort of paradoxical, recursive nature at the bottom. They are self-organizing. They're self-referential. When you come right down to it, they make this sort of paradoxical pointing back to themselves. So the question is, what's the next 150 years of science? I mean, what is it really, right? What is it really? What people really want to know is, when are we going to have flying cars? Right? I mean, you know, they're not interested in the science and information. They want to know when we're going to have flying cars, when are we going to have robots that talk back to us, that can tell us they're smarter than we are, and when we're going to have virtual reality and things where we can just interface by thinking or by gesturing. Well, I'm not going to tell you about those because I don't know. And my point is that those are just individual novelties. Those are just examples like the Chinese of just making new things, like hay or penicillin. They aren't really about the structure of how we discover things. And so what I want to try and talk about is some speculations on the ways in which the scientific method itself may change, and not so much the particular ideas or inventions that it might throw up. So the first set. Well, first of all, I'm suggesting that science will actually change more in the next 50 years than it has in the past 400 years. If we know anything about the kinds of trends and curves that we see, that the actual structure of the scientific method will change more in the next 50 years than the last 400 years. And if you believe that, then you have to go along with me in trying to think about ways in which that might happen. And I think, and basically this will be the context of what I'm trying to suggest, is that most of this will be in the realm in which you all work, which is in the structuring of information and knowledge. That's what this is going to be about. So I might say that Google is about changing the structure of the scientific method in the next 50 years. So, one thing that we know about is it's going to be a biocentury. And here, let me explain what I mean by that. Right now, biology this year has the most funding, the most scientists, is generating the most results that are published. It has the most economic value. It's the most ethically important or relevant in terms of the kinds of questions that it generates. And it has the most to learn. And let me explain that last one a little bit. The living world, the biological world, basically has had 4 billion years of learning. Every day, there's information being generated by biological systems that's being recorded in genomes of these organisms throughout the world. Not just the single ones, of course, but even individuals. It's being embedded into the very ecological systems that we have. It's a vast amount of knowledge and information. If you compare that to physics, it's the same. It's pretty universal. There are deep mysteries about the physics and the understanding of what's underneath the hood in our universe. But the amount of information in physics is actually very small. The amount of information that's embedded in biology is huge. And that's one of the reasons why this is at its point right now where it's become the biggest science that we have, and will continue to be at least for the next 50 years. There is so much to learn. It's so deep. It's so structured. It's so complex. And so the biggest motherlode of information and data in the next 50 years in science, in terms of understanding it, is in biology. Third, computers are leading the third way of science. And I'll take a few minutes to tell you what I mean by the third way. Traditional understanding of science was, there was two parts. There was hypothesis and measurement, observation and theory. Those two went hand in hand, and you kind of try to keep them in balance. You might have a weird idea and you go out looking for data, that was okay, or you might start with the data and try to come up with a theory. But the two of them together were kind of like the 2 feet of science, and this is how the normal understanding of science worked, that you needed to have theories that would predict, make hypotheses that would predict data that you would find, and you had to have theories that were based in some ways that would explain the data that you had. And you try to let neither one outrun the other, but you had a kind of a two-faced aspect of science that required both. So in the measurement side, what's happened is that nothing that I can think of, nothing that anyone else has been able to think of, is growing faster on this planet than information. It is the fastest growing entity on this planet. Hal Varian, whom you're familiar with, did a study of how much information in the world, and he and Peter calculated that it was growing at 66% a year. Physical production, there may be spikes. The iPods may grow at the rate of 200% for a couple of years, but if we talk about anything on the terms of a decade or longer, there is nothing that we're making that's anywhere near the growth rate of information. So information right now is the largest growing thing on this planet. And if you take a chart of the kind of data volume over time, in the beginning, most of the advances were coming through increased precision. And then after a while, we had increase in the spectrum in which we could measure things. You know, we had in the beginning just what we could see, then there were things that we could see through a microscope or a telescope. Then we increased the sources. We could measure things through a thermometer. We could measure other things that we couldn't see. And then over time, we had durations in which we could measure them all the time. For instance, we could measure them longer periods of time, constantly, day and night, for years. And what's happening now, I think, is that, of course, we're adding these technological senses around the world, so we're basically generating huge volumes of information all the time, in real time, constantly, everywhere around the Earth. So I call this zillionics. Zillionics is the field in which you're dealing with zillions of things. Once you get into zillions, a lot of the tools that we have break down, and we're trying to invent ways in which to deal with zillion. And science, of course, is generating zillions of bits of data. These are just some, actually, at this point, kind of old amounts, but you know, terabytes, petabytes, exabytes, we're headed there very fast. Zillionic bytes at some point or other. On the other end of hypothesis, how we learn the things, one of the things that's happening right now is right now this is done kind of with human minds, very handcrafted, but in fact we now have ways to do one type of science is called multiple competing hypothesis. Instead of trying to go through, I'll have a hypothesis about what may happen, I'll try that out, try some things, it doesn't work, okay, I'll make another one, is that you actually make multiple simultaneous hypotheses in which you try to apply data. So hypothesis becomes something that is becoming kind of a mass phenomenon rather than just a single little thing you handcraft. And there are ways in which you can actually try and manage multiple hypotheses as a way to deal with scientific discovery. Another way is combinatorial sweep, and this is what Stephen Wolfram did, which is, okay, the way you explore something is we'll generate every possible variation of it, and we'll explore through that space. And by exploring that space of possibility, we'll know something about what that thing is. So he takes CAs, cellular automata, and they'll make every possible CA and make the whole space of CA and then go through that, trying to discern the characteristics and the behavior of a CA by exploring that possibility space. Well, we can do the same thing with other things, like with combinational libraries and exhaustive search. They're using it in biology right now. They'll make every possible variation of a protein. They'll make every possible variation of a ceramic or a chemical compound. You just explore the possibility space. Again, using robots to make them, to test them. This is something that was not possible before, but we're basically exploring this possibility space of hypothesis by doing it exhaustively in combinatorial exponential expansion. So chemistry compounds, synthesis methods, you make something new, you make every possible way of making it new. And you also generate hypotheses in the same way. Every possible hypothesis that could apply to this situation. Those are the two standard pillars of science: observation, hypothesis, theory. But there's a third one, and that's what I wanted to talk about. The third one is assimilation, or synthesis of those two. You synthesize something. I call it nerd culture, and I did a little piece in Science magazine talking about the usual division of cultures that C.P. Snow talked about, the two cultures, the humanists and humanities on one side and the scientists on the other side. This humanists would explore the human condition by creating, by kind of probing an expression, by, I guess you might say it, examining the human condition, and the scientists would do the same thing by measuring or probing. The third way of knowledge is the nerd way. And the nerd way is that you make something. So the way you study democracy is not by getting in, reading a lot of books about it, or by trying to measure it. The way you study democracy is you make an artificial one. You make a virtual democracy. The way you study a mind is not to contemplate it, to examine it, from all sides, or to try and measure little data points in the brain cell. The way you study a mind is you make an artificial mind. That is the nerd way. It's the way of doing things, is studying things, and discovering things by creating them. Well, simulations has a little bit of that in it. It generates a lot of data. Here's a gamma bay reverse simulation. I mean, it's this huge, spinning off huge amounts of data. And so what this suggests to us is that in the data volume, that most of the data in the coming years is going to be generated by our simulations of things. That actually simulating in the things that we make is actually going to generate more than the natural world. Their efforts in science, that science itself will be generating more data than the natural world measurements do. And so these three, I think science now has a triad. It's now a tripod of three things. It's data, measurement, and simulation. And those three things together are becoming the kind of core of all sciences. So you have data, which is being fed into the simulation, and the simulation is creating new data itself. And then you have the simulation, which also is kind of a theory. And basically, a simulation is a theory that's active. It's an interactive theory. And so theory and simulations become something that feed upon each other. And of course, hypothesis and data measurements the same. And I think that in this intersection of those three is what I call deep science. This is this new science that it has increased data. And we can see this happening in three different arrays. Here, say, complex adaptive science, where you have continuous real-time measurement, which is also being simulated in real time, feeding back to the real-time measurements. The simulation itself creating a continuous search in real time for a hypothesis, which is going on, and the hypothesis, of course, guiding the creation and measurement of data. We can imagine the same thing happening in, say, health sciences, where you have a person who is generating, you have sensors in that person, and they're generating in real time all kinds of information, which is being simulated in real time. And that simulation, of course, itself is feeding into the hypothesis. And so the three of them working together becomes this new science of simulation, hypothesis, and measurement. And of course, we can imagine it happening, say, in the ecological natural world, where we're looking at the real data from nature, we're simulating it at the same time in real time, we're generating real-time hypotheses, which are, again, guiding our measurements and our simulations. This is deep science. So this is the third way of science, where the computer becomes very involved in our method of discovery. It's the third way of science, or not. I mean, It's scary because it has computers at the center, and we're always careful about that. So the last thing I want to talk about science is that it actually will be creating a new way of knowing. Wikiscience is one possibility. The editors of Nature told me that they're expecting to get the first 1,000 author paper this summer. Okay? So that's in traditional science. We can imagine Wikiscience where there's an ongoing document, an ongoing scientific journal article that's never done. It's constantly being updated. It has thousands of contributors around the world. It's open-ended, and it's constantly in flux. That's the nature of adaptive knowledge. Another suggestion is compiled negative results. Right now, negative results are thrown away for the most part. There is one obscure journal that actually has just started to try and report negative results. But negative results can be far more informative than the positive results. Normally, they're thrown away. They're not revealed. And there's actually a move right now to require, in medical studies, that require that the negative results be reported. And the way they're doing that is they're saying that the journals will not publish the medical article of your final results unless you register with them to indicate that you've done the early negative results. So they're hinging the final results of your study being published on the fact that you actually are going to catalog and report your negative results. AI computer proofs is another example in which this is a packing hypothesis. I think it was Kepler did it, suggested at first. It was not proved until recently, and it required an AI help to actually make the mathematical proof. And we're going to see more and more of that as well. And triple-blind emergent trials, this is the idea that you can actually do scientific studies ad hoc by taking real-time data. Imagine if you have a large population of people, you have 24-hour sensory information from their body, temperature, all kinds of things, and you basically extract out of that large amount of data afterwards, you sort out the controls afterwards so that neither the observer nor the researcher nor the scientist actually is aware that there's an experiment going on. The experiment happens after the fact by taking large numbers of variables and extracting out the ones that you want to use and consider as controls. And so finally, distributed experiments is another example, study at home. Other examples where we're taking very small amounts of information and measurements distributed over time, not centralized, and using those measurements to actually correlate and aggregate them. And that's another way. And then the final way is the return of the subjective. And this has to do with science's long-term trend in terms of becoming objective and refusing to consider the subjective. When we get down to fundamental questions like the origin of the universe and things like this, and quantum mechanics, we begin to find that in fact you cannot easily remove the observer, and that you actually have to account for the observer as part of the experiment. And we don't have very good tools for dealing with that right now. And so what we're going to do in the next 50 years is also learn how to tolerate and manage the subjective in science. So those are some speculations on the next 50 years of science. But I'd like to end my talk with just one last thing, which is what I think science means. I think science actually creates a new level of meaning. And one of the interesting things about emergent systems is that actually what's happening is that a new level of meaning comes out of the small parts that were at the lower level. And so if you go back to my diagram of the scientific clustering of information and citations, we can also imagine this web of the internet, which is one of the more current versions of the traffic on the internet. The different countries are different colors. I think North America is blue. But this is a recursive map. This is a map where things are touching back to itself. This is a structure of information. And we can imagine each of those nodes on there as being different species. We can imagine them being different technologies. We can imagine them being different methods of investigation, different styles of discovery. And we can also imagine this as one machine. And so what I'm suggesting is that we have science right now, and the way we're hooking up stuff is that it's actually one very large machine. And I decided to actually treat this as one machine. So I said, if this was really one machine, what would it look like? I'm sorry for this bad formatting, but it has 1 billion PC chips. This machine is right now sending 1 million emails per second, 1 million IM messages per second, 8 terabytes per second of traffic, 65 billion phone calls. It's a huge machine. And in fact, if you were to spec this machine out and try to sell it on Amazon, the processor is got 1 billion chips. It's got 1 megahertz email. It's got 1 megahertz web search, 10 kilohertz instant messaging, and 1 kilohertz SMS. And that's a very big machine. That's a very, very powerful machine. And this is, of course, the aggregate of all the chips and all the machines in all the world. We've created one large machine. Bus speed of 10 terabytes, RAM of 200 terabytes, storage exabytes. Of course, these are all going off the edge just as we speak. But the idea is that is the machine that we're now programming for. We're not programming for your laptop. We're not programming for your cell phone. We're programming for this machine. That is the thing that we're doing. And the other thing about this is that if you take a biological view, it's very close to the complexity of a human mind, a human brain, I should say. It's got a quintillion transistors, and if you take all the transistors and all the PCs in the world, there's somewhere a quintillion of them operating right now. They're all live. It's got it's got 1 trillion on the web. The web has 1 trillion synapses, 1 trillion links, 20 petahertz synapse firings. That's the speed. It has 100 billion clicks per day. So it's a very large brain. So we are this machine, because if we add then to that web machine our own brains, as we sit behind and as we guide the clicks and as we interface, if you add the collective intelligence of the 1 billion people online right now, it's a very large machine and it's a very smart machine. Okay, and so one of the questions that people have is, well, are we going to take off? Is there a singularity about to happen? And I think that I think there is, but I think it's not in the way that Ray Kurzweil and other people would believe, in the sense that there's going to be a rapture or people left behind. I really like this. This is one of my favorite New Yorker cartoons. It says, "Sir, the following paradigm shifts occurred while you were out." I don't think that happens where we will notice things. In fact, I think what's happening is that we'll go through this without really noticing it in this same way. Hey, did anyone notice we're using language? There was never that conversation. People never sat around the campfire and said, hey, actually we're talking. Talking? Yeah. No. That language obviously was a singularity, but we passed through it without really noticing. And I think the same thing is going to happen with this process. So it's what is giving us, what technology gives us is possibilities. People often say technology creates as many problems as it solves, and actually I think it is true. But each of those problems is actually a possibility. And what it gives us is possibilities. So differences, diversity, options, these are the things that technology creates. And it's a great bargain. All of us will always go for that. So each of these nodes in this network is actually possibilities. This is a possibility space, and that's what technology is creating. It's an infinite game, and the idea is to keep the game going. So if you can imagine for the moment Van Gogh being born before the technology of oil paints was invented, or Mozart being born before the piano was invented, or maybe Hitchcock being born before the technology of the film was invented. So there are people alive today whose technology has not yet been invented, whose perfect means for their great genius has not yet been invented. And I think we have a moral obligation to actually create those possibilities so that everybody in the world has a potential to really, really use what they've been born with. And so those possibilities, that quest for the possibilities, is really what technology is about. And I think that's why we're here and why what you're doing at Google is so great, because we're trying to play the infinite game. Thank you. So I'll take questions if people have them. Way in the back.
Through a lot of your talks, you talk about science, but then at the end, you start using the word technology. And that doesn't bother me particularly, but I think if I think about a lot of discussions of the scientific method and so on, and if I look at curricula in colleges, science and technology tend to be kept very separate. Science is much more analytics, technology and engineering is much more synthetic. Do you tend to distinguish the two, or are they all lumped together?
I don't distinguish as much as I probably should, but as I did suggest earlier, I think science is changed much more by its tools than anything else. And so the tool part of science is as important as anything, and is definitely part of the scientific method. So we can change science by creating tools that either measure, or as science becomes more and more information driven, the tools of information become as important as anything else. And so that's why a search engine I would make on that list of some of the most important scientific method inventions some of the most important methods in the invention of scientific method is the search engine, because it's a tool. And it is a technology, but it's actually not as divorced as just other strategies. So I think there is a difference, but not as much as some people think. Yeah.
Science creates a lot of new things, but scientists are not necessarily rewarded.
Right.
Google people made a lot of money, but it's partly because of the great efforts of the later parties that did this model, right? So science is so important, but fewer and fewer people are enrolled in science, and none of the majors. What do you think about that?
So let me repeat the question for those in the back. The question was science is very important, but scientists themselves are not rewarded usually as much as, say, other people who may be involved in technology, for instance. I think that's bad. I mean, I think it would be better if we rewarded them more. And I think some of the move towards in universities to have scientists partake in their inventions through patent arrangements is one way in which society has been trying to reward scientists. But I think in general, they aren't as rewarded. My wife is a scientist. She works at Genentech. She's a scientist there. So I know that scientists, like teachers, don't get the same reward as they should. And I also say are often really badly portrayed in movies. I mean, it just infuriates me to see someone wearing a white lab coat and being crazy. I began this in terms of Back to the Future. So yeah, scientists don't get the respect they should, and I don't know if there's a mechanism to remedy that other than hug a scientist tonight. So right here.
Is there an asymptote to the amount of knowledge that we can reach, either as humans or as whatever becomes of us?
Is there an asymptote to the amount of information humans can reach? Actually, this is another little talk, but I believe that what science really generates is not knowledge, but ignorance. A really good question is a question that would generate more questions than it answers. Okay, so every time we have a really good answer, it will generate 2 or 3 more questions. And I think of those questions as possibilities. And so in a certain sense, while the amount of information is being increased, our ignorance is actually increasing faster. We have far more ignorance now than we did 400 years ago. We have far more questions. We have far more things we want to know about and we realize we don't know about than we did. And so in a certain sense, what science is actually trying to do is expand that frontier space. I often think of it like friction. While the new economy was supposed to decrease friction, so we have a frictionless economy, it did that. But at the same time, at the frontier, at the edges, it was increasing friction. It was increasing the unknown. And so we actually are expanding the unknown faster than we are answering it. And I think that is why. That's because those unknowns are all possibilities. Those are things that we are close enough. They're adjacent. The adjacent possible is what Stuart Kauffman calls it. We now are close enough to see that we don't know that. And that actually is expanding faster than what we know. So I don't think there's an asymptote, because each one of those unknowns is more information. So it's infinite.
You can also look at it as an idea of how much any human can comprehend.
Oh, individually, yes, but we're beyond that. I mean, none of us. At the time when any individual knew everything that was long gone. This is, that big ball, that big machine, collectively is understanding things. And as that happens, we will know as individuals, percentage-wise, relatively less every year. Less of all that's known. Yeah.
It seems to me that you say that that's opportunity.
Right.
Is like all that's usually but in a way you can say that opportunity costs also increase.
Yes.
Because you have to pick one thing and there's so much other things
Right.
that can be possible too.
So the question is that if opportunities are expanding, could we not say that the opportunity costs also expand, and maybe even faster? Yes, I think they do. And here's what I think one of the remedies is that we basically want AI. We want many minds. We want every possible type of intelligence. We want more things seizing those opportunities, and so the costs will increase, but part of what the economy does is it always drives things down at the center. So you have a core where the opportunity costs are less, where friction is less, and at the edges, which are expanding, there's always friction and ignorance, and profit. If you haven't figured that out, profit is related to friction. Okay? There's no profit at the frictionless center. There's only profit in ignorance. Right? Because you have information that no one else has. At the center where there's frictionless and everything is known, there's no profit because everybody knows everything. So that expansion is always happening at the edges where there is high opportunity cost, high friction, high ignorance, and high profit. Well, I guess I've answered everybody's questions. That's great. Thank you for having me. It's really been a real pleasure. Thanks.